topics from 150, 151 that I asked you to review was standard heat of formation, and I am going to cover that here. So standard heats of formation. And this was one of the ways in that course that we used to determine our overall entropy change for a reaction. So delta H, so anytime you hear heats of, it's an enthalpy. In the last video, we talked about heat of vaporization, heat of sublimation, and delta H is what we wrote. So remember, enthalpy is the heat of our reaction. So if you hear heats of, it's just delta H. Because it's standard, I am going to put that not symbol, and then it gets a subscript F for formation. So standard heats of formation. And what this is the enthalpy change when 1 mole of a substance is made from its constituent elements in their standard states. Often it's a hypothetical value because we don't always make things that way, but if we did, what would the enthalpy change be associated with it? So the enthalpy change when 1 mole of a substance is made from its constituent elements, so the elements that make it up, in their standard states. So an example, if we wanted to make water, right? Water is made up of oxygen and hydrogen. So if we wanted to make it from the elements that make it up, right? Its constituent elements, I would take hydrogen, which in its standard state is a gas, right? H2. And then I would take oxygen, which is also a gas in its standard state is diatomic, so O2. To balance it, the number that we get for this, we're actually doing half an oxygen. Remember, we can't have half of atoms. Normally, if we were to balance this, if I asked you to balance this chemical equation, we would put a 2 in front of hydrogen and a 2 in front of water. We wouldn't actually do half, because remember, we can't have half of molecules. It doesn't work. But because we're just trying to get our enthalpy change for it, it's for this ratio. So it actually works okay. I just want to write that so it's a little more legible. So if I want to make water, right, the elements that make it up, so constituent elements, are hydrogen and oxygen. They're both diatomic in gases in their standard state. So standard state, we should probably write that. If you don't remember standard state conditions for thermodynamics, is 25 degrees Celsius. So considered room temperature. So at 25 degrees Celsius, hydrogen's a gas, oxygen's a gas, and then water's a liquid at that temperature. And then generally it would be 1 atmosphere of pressure. And then if it's a solution, a 1 molar concentration. So those would be our standard state conditions for thermodynamics. Be careful, if you're talking about gases, we have a different set of conditions, right? STP for gases is actually 273 Kelvin, so 0 degrees Celsius. So this is for thermodynamics, which is different than for gases. So the amount of energy, back up to our example here, that it would take to make water, right, my enthalpy change would be delta H subscript F with my little not symbol. So my heat of formation for hydrogen itself is 0. Remember, our definition is that we're making it in its standard state from its constituent elements in their standard states. So I'd be making H2 from H2. So my enthalpy change would be 0. My enthalpy change for oxygen is also 0, right? O2 is its most standard state. And then if you were to look up the standard heat of formation for water, and there is an appendix posted on Canvas under the Chapter 6 module that has some of these numbers, but it comes out to be 85.83 kilojoules per mole. So what this is saying is if I was to make water from hydrogen and oxygen in their standard states, this is the amount of energy that it would take. And actually, because it has the negative, right, it takes a negative amount, that means it's being released, right? Anytime we have a negative value, it means my final is less than my initial. Most of these are going to be negative values because most of them are going to be combination reactions. Remember in the last video, we said if it's a combination reaction, they tend to have negative enthalpy changes, right? We're forming bonds. Because I'm forming bonds, I'm releasing energy because those bonds are stabilizing. What we use these for is we can use it to determine our enthalpy change for our reaction. So we can use our heats of formation, and we would just get those values from that appendix that's posted on Canvas, or I would provide them to calculate our enthalpy change for our reaction. It was one of the 3 ways that we did it in 150, 151. We used bond dissociation energies, we used standard heats of formation, and then we also did it using Hess's law. That was the one saying that if a reaction goes from reactants to products in more than one step, then the enthalpy change, there's an enthalpy change for each of the individual steps, and if we add them together, that gives our total enthalpy change. So heats of formation, one of the ways that we did it in that class. So my enthalpy change for my reaction would be the sum, so my sum symbol, the sum of my heats of formation for my products minus the sum of my heats of formation for my reactants. An example for us, we're going to calculate the enthalpy change for the following reaction. So I have C2H4, which is ethylene, and that's a gas, and we're reacting it with 3 oxygen, also a gas, to produce 2 carbon dioxide gases, plus 2 water gas. So a combustion reaction for us. Remember, combustion reactions was when you took some sort of fuel, usually carbon and hydrogen are involved, sometimes oxygen. It doesn't have to be that, but generally it is carbon-based. We add oxygen to it, we get carbon dioxide and water as our products. So what we would need to do is we would need to look up our standard heats of formation in the appendix that I do have posted on Canvas. So in Appendix G is how it's labeled on Canvas. I'll write them down here for us, but if they're not provided, we want to look them up. Do be careful to pay attention to the states of matter. It's going to take a different amount of energy to make water in the gas state than it is water in the liquid state. So pay attention. Water is going to be on there more than once. Once as a liquid, once as a gas, and then once as a solid. So pay attention to states when looking them up. Right? States of matter. Being lazy when I just say states, but states of matter. It's going to matter if it's a solid, liquid, or gas when you look up those values. So I'm going to write them down for us. So for C2H4, it is 52.5 kilojoules per mole. This one is not negative. I said they're usually negative, but not always negative. Oxygen, what's oxygen going to be? Remember what my definition is, right? I'm making this compound, right, O2, from its constituent elements in its most standard state. So I'm making O2 from O2. My enthalpy change, right, is going to be 0. My enthalpy of O2 is the same as my enthalpy for O2. So when you subtract them, we get 0. The reason I mention this is if you had this problem on a test and I was giving you the values, I won't usually even list oxygen. I'll just leave it off. And then I always have students wonder, well, you forgot to give me information. I didn't. I'm just testing you onto whether or not you know that you need to have it or not, right? I want you to know that if you're forming something that's just an element in its standard state, its standard heat of formation is always going to be 0. We'll list it here just for completion and to make my point, but do be careful. So for carbon dioxide, a negative 393.5 kilojoules, and then for water in its gas state, a negative 241.8 kilojoules per mole. And again, be careful on the states of matter. I know I've said that a couple times, but really be careful. If I go back up here and I look at my value for water when it was a liquid, right, that's a different number than my value down here when it's in its gas form. And if you do the problem with the wrong number, you're going to get the wrong answer, so do be careful. So setting up the problem, I do need to pay attention to my coefficients, right? These are the enthalpy changes for 1 mole of that substance, right? Kilojoules per mole, there's a 1 on the bottom. These coefficients mean I have more than 1 mole. So I have 1 ethylene, but I have 3 oxygen, 2 carbon dioxide, and 2 water. So I do need to multiply the corresponding standard heat of formation by the coefficient. So for carbon dioxide, I need to take its number from below and multiply it by a 2. And then remember, we're doing sum. So sum of the products minus sum of the reactants. So products first. So carbon dioxide, there was 2 of them. So I'm going to take a 2 and multiply it by a negative 393.5 kilojoules per mole. And then sum, so I'm going to add to that water, which has a coefficient of 2 also. So 2 times a negative 241.8 kilojoules per mole. And then that all gets added together, so some brackets. And then from that, I'm going to subtract 1, because I have 1 mole. So 52.5 kilojoules per mole. And anything times 0 is just going to be 0, but I am going to add it here just so you can see. I don't want, if you have one where it's not 1, I don't want you to like skip it. I want you to see that it's the sum of all of them. So I'm going to throw the 0 in there, even though mathematically it makes no sense. So kilojoules per mole. And I'm just making it smaller so you can see the brackets because I ran out of room. So sum of the products minus the sum of the reactants. So the biggest mistake that I see students make on these is honestly just the math. So be careful. The first one, I have a negative value, and then I'm going to add another negative value to it. And then I'm going to subtract a positive value in this case. It could be subtracting another negative value. So just watch your signs when you plug this into your calculator. So I'm going to grab my calculator and plug it in here. Again, just be really careful with your signs. You have negative numbers and you have positive numbers and you have addition and you have subtraction. And often something that seems so simple is what throws people off. And I end up with my overall enthalpy change to be a negative 1,323.1 kilojoules per mole. Because it's addition and subtraction, those coefficients are exact numbers, so they're not going to count for significant digits. Remember, when we're adding and subtracting, it's the number digits after the decimal point. So I have 1 after the decimal point, 1 after the decimal point, 1 after the decimal point, so I don't want 1 after the decimal point in my answer.